Okay, so it's a pleasure for me to introduce Kiran Kedlaya from the University of California, San Diego. He will talk about towards explicit realizations of the Sato-Tate group of abelian threefolds.
All right, let me start by thanking Victoria and So-Young for the introduction and for organizing this virtual conference. This is, of course, not going to be the last virtual conference that many of us attend because things might be different for a while. But even after it's possible to travel again, I hope our community continues to explore the possibility of using technology to, for example, reduce our carbon footprint and make talks accessible to people in locations where they might not have access to physical conferences. So with that, let me go ahead and start. As I said in the break beforehand, the slides for this talk are posted, in addition to being posted on the conference website and on research seminars, they are also posted at my website. I have both the display version and the handout version, depending on what you prefer. I should also mention that this is part of a joint project with Francesc Fite and Andrew Sutherland. I reported on this last summer at the AGCT conference. If any of you were there, you will have heard some version of this story with some of these slides before, but there is new material. So you will learn something new. If not, let me start by running through some basics. So this story is about Sato-Tate distribution. So let me just maybe fix some notation. So initially, if I have an algebraic variety over a finite field, its zeta function is defined as either an Euler product in the style of the definition of the Riemann zeta function or a Dedekind zeta function, where you index over closed points of the scheme X, which is the same thing as Galois orbits of FQ bar points. But since everything is over FQ, you can sort of consolidate and rewrite things in a different way. You can write this as a sort of modified generating function of the sequence of point counts of X over all of the extensions of FQ. Those are, of course, indexed by positive integers. So this is modified in some way so that it agrees with this. And so in particular, it has integer coefficients, which is clear on this side. So this expression generalizes things that were seen in elementary number theory, and at various levels of generality. This was considered ultimately by Weil at this level of generality. And he observed numerically, and then this was proved later, that when X is smooth and proper over FQ, this thing factors as a rational function. So you have denominator factors and numerator factors, and each factor is distinguished in a certain way. It's reversed from the way this is maybe normally defined. But in this talk, I'm going to use this orientation. I'll call these things Q to the IV polynomials. So they have, if integer coefficients, they have constant term 1. So this is the part that's backwards. If you're used to Frobenius characteristic polynomials, those would have leading coefficients 1, but these are what you might call L polynomials. They have constant coefficient 1, and they have roots of prescribed complex absolute value. The roots of pi all have complex absolute value q to the minus I over 2. So again, this minus is because I'm reversed from Frobenius characteristic polynomials. So you might think about the example of an elliptic curve, which you maybe have seen, where the denominator has 1 minus t and 1 minus qt, and then the numerator is a quadratic polynomial that reflects the number of points over fq. Well, that generalizes to any curve of any genus, which is supposed to be nice, meaning the stuff in parentheses. So the denominator will always consist of these two factors. The numerator will have degree 2 times the genus, and it will be palindromic. And the condition on the absolute values will guarantee that the coefficients are bounded. So for example, in the elliptic curve case, the middle term is bounded by 2 times square root of q in absolute value. That's the Haas estimate. Similarly, when X is an abelian variety of dimension G, we've heard a lot about abelian varieties over the past 2 days. When X is an abelian variety of dimension G, the P1 will be of degree 2G and will be palindromic. And the other factors will be what I call exterior powers of the P1, which is to say if P1 has roots alpha 1 through alpha 2G, then PI has roots which are I-fold products over distinct indices. So if P1 is the reverse characteristic polynomial of a linear transformation on a vector space, PI is the characteristic polynomial, or reverse characteristic polynomial of the induced linear transformation on the ith exterior power of that vector space, hence the terminology. And crucially for this talk, if you can consider a curve and its Jacobian, they will give you the same P1. So the zeta function of a curve is reflected in the zeta function of its Jacobian, in the sense that the P1 is just transferred over and the other terms change because for an abelian variety, they have to satisfy this alternate relation. Well, the P0 doesn't change, but for example, the P2 changes because it goes from being degree 1 to being degree 2G choose 2. But the P1 remains the same when you pass from a curve to its Jacobian. Okay, so this was all over finite fields, but we're interested in abelian varieties over number fields. And so if A is an abelian variety over number field K, and the ring of integers of K is denoted OK, then I'll consider the L function. I'm only going to consider the good reduction factors because I'm going to be asking questions that are not sensitive to the bad reduction factors. So this is an incomplete definition. So this incomplete L function is the Dirichlet series that I form by running over primes of OK that are of good reduction for A, where A should extend to an abelian scheme over the localization at this prime ideal. So I take the factor P1 of the reduction modulo P, which does not depend on choice of a model. So I take that LP and I substitute in the absolute norm of the prime ideal P to the power minus S. And then I take the inverse of that and I take an Euler product indexed by these things. So for example, if A is an elliptic curve over Q, this is the usual expression. This thing comes from the usual numerator of the zeta function of an elliptic curve, where AP is P plus 1 minus the point count over FP. And so I get this product, but this thing was in the numerator before, and now I put it in the denominator to form this Euler product. And this has some region of absolute convergence, where when the real part of S is greater than 3/2. It is expected to admit a meromorphic continuation to C, and you can say more than that. I won't go into the details either of what this analytic / meromorphic continuation looks like, or in what cases we know, because that's a quite rich story that's tangential to my talk. But I will just say that, for example, for an elliptic curve over Q, we know analytic continuation for this thing, and that was proved by Wiles in the semi-stable case and Roy Conrad, Diamond, Taylor in the general case. So let me articulate the question that we're going to be concentrating on in this talk. So let me renormalize the change to the so-called analytic normalization by rescaling the L polynomial. So now I've kind of destroyed the arithmetic information that was in this L polynomial, because I've renormalized so that I no longer necessarily have integer coefficients, but now I have coefficients that are uniformly bounded, independent of the choice of the prime ideal. So it makes sense to ask statistical questions. This point, the point given by, well, I only need the first G coefficients in order to reconstruct the others. So it's natural to think of the first G coefficients as defining a point in G-dimensional Euclidean space. They lie in a bounded region. So then it's natural to ask whether these points have made a limiting distribution, and if so, what this distribution is and how it can depend on the elliptic curve, or the abelian variety in general. For an elliptic curve, conjecturally, there are 3 possible distributions. We've seen this trichotomy earlier in the conference. There are cases when E has CM defined over the base field, when E has CM not defined over the base field, or when E does not have CM at all. And in each of these 3 cases, what you see as the distribution for the one coefficient that is at issue is the trace distribution from random matrices sampled from some compact Lie group. And in the three cases, it's the circle group, the normalized of the circle group in SU2, which has two connected components, or the group SU2. And if you have never actually looked at Drew's webpage, you should look at the animations of this on Drew's webpage. Maybe I'll skip them for the sake of time, but because this is a virtual conference and you're on a computer, you can easily click over and watch these animations in another window as I continue. All right, so I'll briefly say this. This recaps something that Grzegorz talked about in much more detail in his lecture. If we assume the Mumford-Tate conjecture for the abelian variety A, which I'll refer you back to the earlier lectures to understand what that says. But in the cases I'm going to be interested in, this is an empty assumption because the Mumford-Tate conjecture will be known. Then there is a construction, which I won't recall right now, but you've heard about it earlier. There is a construction of a compact Lie group contained in the group of unitary symplectic matrices of size 2G, so G equals 1 in the elliptic case. Then this would just become SU2, but we'll be talking about G equals 2 and 3 later. So there's a compact Lie group I can define, and then for each prom ideal that I was considering, a conjugacy class with the correct characteristic polynomial, the one that governs the normalized, that corresponds to the normalized L polynomial, and the generalized Sato-Tate conjecture, which goes back to Serre in this form, is that these conjugacy classes are equidistributed with respect to the image of Haar measure. So in particular, the characteristic polynomials are equidistributed with respect to the image of Haar measure. But there's, strictly speaking, more information contained in the equidistribution statement for the Sato-Tate group than at the level of characteristic polynomials. And I'll make a remark about that later. This reduces by an argument that goes back to Serre, which is secretly just the proof of the prime number theorem by Adamar and Delavalle-Poussin. This reduces to a statement about analytic continuation of the L functions associated to irreducible representations of the Sato-Tate group. And as I mentioned, there are certain cases where we know this analytic continuation statement. For example, if A is an elliptic curve over a totally real field, as was mentioned earlier, then the analytic continuation is known by potential modularity theorem. In fact, even if the base field is a CM field, is a more recent result by a 10-author collaboration that proves the same thing. But let me not go into that because for the purposes of this talk, I'm not actually going to make any statements that depend on whether or not the equidistribution is known. I'm going to be making statements about what the Sato-Tate group is, and the definition of it will be unconditional in the cases I'm interested in, because I'm going to restrict to cases where the dimension is at most 3. So the Mumford-Tate conjecture is known because of endomorphisms. It's sort of the simply trivial cases of the Mumford-Tate conjecture. And in these cases, as Edgar mentioned in his talk, the Sato-Tate group is determined by things that can be computed rigorously. So the Sato-Tate group is determined by the endomorphism algebra of A over an algebraic closure of Q, base extended all the way up to the real numbers. So you view this as an algebra over the real numbers together with an action of the absolute Galois group of Q over the base field. And then this data determines the Sato-Tate group, and these are all things that you can compute in using techniques that Edgar discussed earlier. So this Sato-Tate group contains information. Again, this is something that Grzegorz talked some about in his lecture, but let me say this again just to reinforce. The Sato-Tate group is a compact Lie group, but it's not necessarily connected. So it projects onto a finite group with a connected kernel. So there's a canonical exact sequence that separates the connected part on the left with the component group on the right. And the connected part depends only on geometric data. It only depends on A after its base change to an algebraic closure. It's equivalent data to taking the Mumford-Tate group, which is determined by the Hodge structure, as Mark discussed. You take the Mumford-Tate group and you forget the fact that it's an algebraic group over Q, you base change it all the way up to Q bar. And then it's essentially the same data as this. So you lose some information relative to the Mumford-Tate group, but but it's similar data to the Mumford-Tate group. And in particular, if you have the Mumford-Tate group, you can identify what this connected part is going to be. The finite part is obviously going to be where the arithmetic is hidden. It will be canonically identified with the Galois group of a certain finite extension of the field K. And in cases where the Mumford-Tate group is explained by endomorphisms, which is true in all cases of dimension at most 3, this field extension L over K will be what I call the endomorphism field. It is the minimum extension of K for which the endomorphisms of A over L are the same as over Q bar. So it's the minimum field over which all geometric endomorphisms are realized. So for example, if A has dimension 1 and A has Cm by a quadratic field not contained in K, call that field M, then the endomorphism field is the compositum of M and K. And this component group is, on one hand, it's the component group of N of U1, which has 2 components, but on the other hand, it's canonically identified with the Galois group of MK over K. Of course, there's no ambiguity about the identification of this case, but in more complicated cases, I should emphasize that there is a canonical identification of this quotient group with the Galois group of this extension. All right, at this point, I'm going to pause and see if there are any questions. I don't see any in the chat, and I don't see any in the Q&A, but I'll pause for a moment to see if anything comes up. Okay, I don't see anything.
I think so far so good. Can
All
continue?
Right. I'll continue then. So let me talk about abelian surfaces. So we talked about genus G equals 1 for a little while. Let me say a little bit about G equals 2, as was alluded to earlier. This is covered by a theorem from a joint paper from 2012 with Francesc and Drew and Victor Rocher. So we proved that there are 52 possible conjugacy classes of closed subgroups of USP4, which occur as Sato-Tate groups for some abelian surface over some number field. So if you allow all possible choices of the number field and you quantify over all possible abelian surfaces and you divide by conjugation, because this construction is only going to be well-defined up to conjugation within the USP4, then you get 52 possible answers. There are exactly 6 different possibilities for the connected part. I'll list them on the next slide. The component group can be as large as 48. All the possible orders of the component group divide 48, and there is one that is this big, so this is a sharp divisibility upper bound. The 52 cases can be distinguished by looking at the distinct distributions of LP bar. However, I should emphasize, LP bar has 2 unknown coefficients, A1 and A2, and you do not get distinct distributions if you only look at A1. You get somewhat fewer. I don't remember exactly how many, something in the 30s. Drew says it's 36, thank you. And again, I won't link to this page again, but you can look at all of these things on Drew's webpage. He has animated histograms of examples of all of these distributions. As I mentioned, this theorem is quantified over all number fields K. You get a different answer if you only consider K equals Q. In that case, only 34 of the 52 cases can occur. If you allow totally real base fields, then a 35th case becomes possible, but the remaining cases require other base fields. You can, for example, use imaginary quadratic fields to get some of them. So this was a question that was raised by Sarah, and Francesc answered it in a joint paper with Chevy Guitar. There is a choice of field K over which all 52 cases occur. This is a certain biquadratic extension that they construct, or polyquadratic. It's compositum of, I think he needs to take 6 quadratic extensions or so. So it is possible, so there are no mutually exclusive conditions. You could imagine that certain things could only happen over fields that do contain a certain quadratic extension and certain other things that only happen over fields that don't contain that quadratic extension. Nothing like that happens in this case. There is no condition that makes it impossible to. Yes, so Francesc confirms that it's a degree 64 polyquadratic in this case. And so I phrased this over abelian surfaces, but you could also quantify over principally polarized abelian surfaces or even Jacobians. And we show that nothing changes. You don't lose any cases by making this further restriction. And we even give explicit examples of genus 2 curves whose Jacobians are provably giving rise to these 52 cases. So everything is the same, depending even if you restrict to Jacobians. And as I mentioned, the P1 of a curve and its Jacobian are the same. So you can define the Sato-Tate group of a curve. It will be the same as the Sato-Tate group of its Jacobian. So there is nothing lost by doing this. I should also mention in passing, because this is related to Edgar's talk, the Sato-Tate group of an abelian surface is also related to the Sato-Tate group of its Kummer. I think the connected part is certainly the same. You might lose a factor of 2 when you go to the Kummer surface, because the Kummer surface involves the division by 2. But in any case, they're very closely related. So this can also be thought of as giving a classification of Sato-Tate groups of Kummer surfaces, and it's closely related to the Sato-Tate groups of K3 surfaces of large Picard number, but let me not say more about that. Right, so I promised you the connected part. So here's a little table that summarizes what can occur in terms of, remember the connected part of the Sato-Tate group is going to be determined by the endomorphism algebra, the geometric endomorphism algebra of A, base extended from Z to R. So there are 6 possibilities for that. The trivial endomorphism ring would give rise to the first line. And so these are the 6 possibilities for the connected part of the Sato-Tate group. And then the extensions, as you see, you get more and more extensions as the dimension of the Sato-Tate group gets smaller. So in this case, you have a diagonal embedding of the one-dimensional CM case. And so this gives you the most possibilities, because somehow this thing is so small that it has a rather large normalizer. So there's lots of room for finite extensions in here. Of these, I've picked out the ones that are maximal with respect to inclusions of finite index. So I've enumerated here, and I should include a warning that because I'm doing a base extension from Z to R, not from Z to Q here, even if A is geometrically simple, its Sato-Tate group can look, so to speak, decomposable. For example, if A has CM by a quartic field, then the real endomorphism algebra is K tensor over Q with R. That splits as C cross C, as if A were decomposable, even though it isn't. So, so you lose information about decomposability when you look at this somewhat coarse level. But what you gain is the fact that you have a finite number of options to choose from. So the classification turns out to be something that can be sort of stated in a finite way. Okay, so this is everything about surfaces. So this talk is mostly about threefolds. So somewhat more recently, Francesc and Drew and I have succeeded in classifying Sato-Tate groups of abelian threefolds. The delay was due to the fact that there are many more cases. There are 410 conjugacy classes of closed subgroups of USP6, which occur as Sato-Tate groups for some abelian threefold over some number field. So this is exactly analogous to the box theorem from 2 slides ago, but all of the bullet points below will look different, and some of them will not be as satisfying. So first of all, there are 14 options for the Sato-Tate groups of abelian threefold. So I put I mentioned a paper of Monin and Zarhin here, but this might not be the earliest reference for this. I mentioned this paper because it gives a really nice compact description of essentially what effectively are connected parts of Sato-Tate groups in all dimensions up to 5. They're not using that language, but it's effectively, it's equivalent to, or it implies that classification. And I'll show you the options on the next slide. The order of the component group can be somewhat larger than it was before. So there are options of size 192, 336, and 432. Notice these only have 2s, 3s, and 7s in them. So there are no factors of 5 that can occur. And these are divisibility bound. So all of these, all of the orders divide one of these. This refines earlier estimates. So the first upper bound on this order was given by Silverberg, and then a sharp divisibility upper bound was given in joint with Guralnick, but it was the LCM of these 3 quantities. And so this is a sharper result because it picks apart exactly which numbers, it's a sharper upper bound when right, because you can't get 2 to the 6 times 7, for example. Here's a difference with the case of surfaces. The 410 cases only give you 409 distinct distributions of characteristic polynomials, even if you count all 3 distinguishing coefficients. So there are in fact there are 2 cases that cannot be distinguished at the level of polynomial distributions, but they can be distinguished by looking at other representations. And in fact, you can even distinguish them by looking at the isomorphism class of the component groups. So the component groups in these 2 cases both have order 54, but they're distinct groups of order 64. So they can be, if you compute the endomorphism fields, you would see the difference that way. We have not made any attempt to understand what happens if you restrict K. So we do not know how many of these cases occur over Q, for example. This is a problem an open problem of some significance to try to understand what happens over Q. But as you can imagine, there are 410 cases you have to go through, so it might be quite difficult. It's also unclear what's going on with restricted versions where you insist on principal polarizations and Jacobians. So I think in my HSET lecture, I claimed that everything could be realized by a principally polarized abelian threefold. I believe that's false, although we haven't proved it yet. I will say later what appear to be obstructions to achieving things with principally polarized abelian varieties. That would certainly also obstruct Jacobians. So part of the goal of this talk, and what I'll spend most of the rest of the slides on after this one, is to talk about explicit realizations. And there we will see some cases where you hit principally polarized abelian varieties, in some cases where you hit Jacobians, but we do not have a complete story. Sorry, I have this table of possibilities. So I'm going to be referring to these labels. So here's a good opportunity to use the fact that you can look at these slides in another window. I recommend keeping this slide visible in another window as I continue the talk, because I'm going to refer to these labels for these 14 cases because these are hard to fit on the slides when I'm doing a lot of text. I'm also not going to write these endomorphism rings out. So I'm going to use these labels as a convenient shorthand, but to make them less opaque, I suggest keeping this slide visible. You can see that there are many extension groups when the group is U13. This is somehow maximally CM. These correspond to abelian threefolds, which are isogynous to the cube of a CM elliptic curve. And you can see there are also many maximal groups that occur with respect to inclusions of finite index. So most of the work in proving this theorem is classifying these cases because, again, the normalizer of this group is quite large. It is not finite, so you have to identify finite groups that satisfy some auxiliary rationality condition, which I won't talk about. So I won't say anything more about where these 171 groups come from, but this is the table that I'm going to be working off. So let me pause again to see if there are questions. I still don't see any in chat. I don't have the window open to see if any hands are raised. don't see any hands raised either. All right, so I will go ahead and continue. All right, so let me step through the cases, the 14 connected parts, and then kind of discuss the situation for, particularly for maximal Sato-Tate groups with a given connected part. Because I didn't say this explicitly on an earlier slide, but I sort of suggested this. If you start with an abelian variety over a number field and you do a base extension, you don't change the connected part, and you reduce the component group precisely by the effect of Galois. The Galois group that you start with becomes the Galois group of the compositum over the new field. So it's very easy to read off, once you know the Sato-Tate group of an abelian variety over number field, including the Galois interpretation of its component group, it's very easy to see what happens at the level of base extensions. So in particular, to solve the problem of realizing, giving explicit realizations, as long as you don't care about base fields, it's enough to worry about maximal cases, at least if you expect to be able to realize all of the maximal cases. Once you start running into obstructions, then you have to worry about what are the maximal groups that are unobstructed. I won't get into that level of detail in this talk, but that's a question for subsequent work. So for each candidate, I'm going to try to identify maximal candidates and describe realizations of these maximal candidates by abelian threefolds. And in fact, all of the candidates that I write down will be over Q, but of course the base extensions will not be. Many cases, these will not be Jacobians. I'll have to circle back to try to get Jacobians. But if I'm not worried about Jacobians, I can give a rather concise, although compressed, description of how to hit all of these maximal candidates. So let me start with the easiest cases. I'll say that G circle is indecomposable if it's USP6 or U3. That means I'm talking about an irreducible three-dimensional representation. There are very few extensions in these cases. USP does not admit any extension in itself, and U of 3 emits only the normalizer, which has index 2, just like for genus 1. USP occurs for an abelian threefold with trivial endomorphism ring, which is to say pretty much any abelian threefold you can write down. But conveniently, it's relatively easy to write down an explicit example. So Zarhin proved that the Jacobian of y to the 7th minus x plus 1, this hyperelliptic curve gives you an abelian threefold with trivial endomorphism ring, and therefore it realizes USP6. So the case NU3 is not that much harder. It's what you get for the Jacobian of a generic Picard curve. So I'll write P4 to mean a polynomial of degree 4. And a generic, of course, implies it should have no repeated roots. So to take a concrete example, let me consider y cubed equals x to the 4th plus x plus 1. This example appears in a paper by Margaret Upton. She shows that by counting Frobenius elements, she uses essentially the faulting-Serre method to show that the Jacobian of this thing has maximal mod 67 Galois image. And therefore, this thing has maximal 67 attic Galois image, which implies that the Sato-Tate group is NU3. In fact, you can also show that it has maximal mod 2 Galois image by computing directly. This will come up later, so I mentioned it explicitly. The Galois image here can be read off from the 27 odd theta characteristics of the Jacobian, which corresponds to the 27 bitangents of this thing, which is a little confusing because there are 28 bitangents of a plane quartic, but one of them is the line at infinity, which doesn't move under Galois. So it's the 27 other bitangents that you care about, and their Galois image gives rise to the mod 2 Galois image of the Jacobian. So in this case, you can see that the mod 2 Galois image is maximal by computing that the 27 bitangent lines are defined over the maximal possible extension they could be defined. Okay, so now we've got two cases where we have Jacobians. So for the rest of this section, let me not worry about Jacobians. So I'll talk about split products next. So split products are cases where you can write the thing as a product with no shared factors between the two sides. So that includes some cases where there are repeated factors because there's another factor that you can put to the other side. So for U1 cross U1 cross SU2, you put the two factors of U1 on one side, you appeal to the theorem about abelian surfaces to understand what happens in the case U1 cross U1, and then you product with what happens for SU2. So more precisely, the normalizer of G circle in this case splits. And so you're solving a classification problem for lower dimensional abelian varieties. And in fact, this is also how you make the maximal candidates. You just take maximal candidates from lower dimension and multiply them together. So at the level of principally polarized abelian varieties even, there's nothing more to be done to solve the realization problem in these cases. But these are not going to be Jacobians in general. So now there are what I call triple products, where you have 3 copies of the same group. There are 2 of these, of course. So in these cases, the normalizer of G circle is finite. So the only possibilities for an extension are going to be subgroups of this normalizer. So in the non-CM case, the normalizer is S3. You just shuffle the factors however you can. This is very easy to get with a principally polarized abelian variety. You take a Veil restriction of a non-CM elliptic curve over a non-Galois cubic field. So it's not a Jacobian a priori. Well, it's not a Jacobian because it's decomposable, but it is a principally polarized abelian threefold. Now for U1 cross U1, things are a little more complicated, because if you know the paper about abelian surfaces, it's not the case that arbitrary subgroups of the normalizer actually appear. There are some restrictions that come from Shimura's theory of CM types. And so the maximal permissible candidates for G are much smaller than the normalizer. The normalizer in this case would be the Reith product of C2 by S3. Here you get a much smaller set of candidates. You just get C2 cross C2 cross C2, or C2 cross C4 and C6. The first 2 cases, it's easy to see how they occur as products by taking lower dimensional CM abelian varieties. The C6, of course, occurs for the Jacobian of y squared equals x seventh minus 1. That gives you a hyperelliptic example. Or this curve y cubed equals x fourth minus 1 has a C9 action. So that's a Picard example. So you do get Jacobians in these 2 cases. But in the other 2 cases, I have to do something else to get Jacobians. I'm only getting principally polarized things. Finally, there are the triple diagonals, where I took an SU2-3 or U1-3. In these cases, the normalizer is infinite. So there's not an a priori bound that tells you that the finite groups just come from some given finite overgroup. So here you have to do work to solve the classification problem using what's called the rationality condition, which I won't talk about. Let me just tell you how these cases are realized in a uniform way. You start with an abelian threefold who's isomorphic. Sorry, it's only I should say isogenous here. Yeah, this is important. This should be isogenous because I'll tell you why in a moment. So it's isogenous to the cubic elliptic curve with rational endomorphism ring, either Q or the imaginary quadratic field M, which will, in all cases of interest, will be class number 1. So this actually can be done over Q. So what I then do is I form an appropriate Galois cocycle valued in the geometric automorphism group, and then twist by that. And this will sort of give me only the projective image of this thing will show up, but I will sort of realize a group using this projective image. Now the issue here is that I made another mistake on this slide. This should be, oh no, this is correct as written because this should be isogynous. So if you only consider things isomorphic to a cubic elliptic curve, this automorphism group will look like integral 3×3, invertible integral matrices over M. So you have GL3 over OM. But in some of the cases, we don't get groups that I can realize in an appropriate way over GL3 of OM, especially when I need to put in the Galois conjugation. So we do some cases where we have things that are isogynous, and so you end up in some other Eichler order. But everything can be realized over Q, so that's okay. And where's the problem with polarization? So you can compute an induced polarization on one of these things by averaging, right? You have you have a positive definite, you have a Hermitian form that you average. The average of a Hermitian form is still Hermitian. This is Weil's trick. So you still get a polarization on the twist, but in general, it won't be principal. And so you can actually calculate using some work of Fite, you can calculate what these polarizations are and what their degrees are, and in general, they are not, in fact, principal. So this is where I believe the obstruction is going to come from to realizing some of these cases with principally polarized abelian threefolds, but I don't know for sure that this is actually an obstruction. So, okay. So let me talk a little bit about type N, but I need to keep this moving because time is short. So the 12 groups of type N mostly come up as complex reflection groups, twisted by, or semi-direct product by the Gal of M over Q. This makes it easy to make Galois cocycles because the inverse Galois problem is easy for complex reflection groups. The invariant ring of a complex reflection group is a polynomial ring. And in fact, if and only if, I think this is due to Shepard and Todd. So these are precisely the cases when you can solve the inverse Galois problem generically in a trivial way. But you can also find explicit Galois embeddings. Notably, one of these groups, the complex reflection group, is a lift of the Hessian group of collineation, of sort of dimension 3 collineations. This is a group of order 216. This thing you actually get by taking the mod 2 Galois representation of a generic Picard curve, like the example I mentioned earlier. So that example actually helps you later. Okay, so here's the score, and let me leave this. So this is what we've done so far. We've realized these two cases of Jacobians and one CM case, and basically nothing else so far. So I'll show you more. We'll iterate this later, but let me pause and see if there are questions at this point.
I think so far we're good.
Okay. Maybe people are holding questions until the end. So, okay. So let me talk about a simple construction of Jacobians that will give you a lot of examples of realizations. So one way to convert project constructions in Jacobians is to glue along two torsions. So this goes back actually to Jacobi at some level for gluing pairs of elliptic curves. But this was, but let me focus on genus 3. So I mentioned two results. One is a beautiful result of Howe, Lepreveau, and Poonen that tells you how to glue triples of genus 1 curves. Well, really, they're Jacobians. So if you have 3 elliptic curves, let's say, because this is really gluing elliptic curves, the product of whose discriminants is in the trivial square class, then it's not quite the case that you can write down a 2-2-2 isogeny between the product of their 3 Jacobians and A. You can do that geometrically, but over K you have to twist you have to take a quadratic twist of the Jacobian before you can do this. This is okay because quadratic twists do not affect the Sato-Tate group. So the Sato-Tate group of A really will be a product. But arithmetically, you do have to put in this twist. But they tell you what the twist is. That you can compute. They give you explicit formulas to compute the curve, this Jacobian, this curve, and the twist. More recently, there's a PhD thesis that's maybe almost submitted by Jeroen Hanselman that does similar thing for a genus 1 curve and a genus 2 curve. I should mention this. This is an extension of an earlier paper of Ritzenthaler and Romagny that sort of gives a partial result along these lines. So what Jeroen Hanselman does is he tells you how to glue a genus 1 curve and a genus 2 curve. There is, again, a matching restriction. You have to have a rational point of 2 torsion on the Jacobian of the genus 2 curve. And when you take the perp of this 2 torsion subgroup modulo itself, you have to fix an isomorphism of that with the 2 torsion of the genus 1 Jacobian. And then you can write down a similar gluing. And again, this is done explicitly. So you can do this in Magma code. So let me tell you one very beautiful example of the gluing of Howe, Lepreveau, and Poonen. So this is an example that I essentially I ordered from Everett Howe, and he was able to deliver. So consider the following 3 CM elliptic curves over Q. So they have CM in 3 different quadratic fields. these three different quadratic fields are rigged up so that the discriminants actually multiply to a square. It's a lucky coincidence that you're able to do this over Q. It's just lucky that this is possible. But because this is possible, the product of these three things is isogenously to a twist of the Jacobian of this curve. And therefore, this curve gives me a Jacobian whose Sato-Tate group is a maximal extension of U1 cross U1 cross U1 with component group C2 times C2 times C2. There are a few other triples that you can rig up that do this, but they're all, it's a finite set of choices. So you don't get a lot of examples this way. I think I maybe get 16 curves this way. I should also mention the SU2 cross SU2 cross SU2, the extension of that by S3, you can also achieve, you can also take a Weil restriction that I mentioned earlier and make that 2, 2, 2 isogenoous to a Jacobian, maybe up to a twist. Actually, I think you can avoid the twist in that case if you're careful enough. So these triple product cases you can handle by gluing triples of elliptic curves. You can glue, there's a very simple instance of the gluing construction that I mentioned earlier. This is I don't know who to attribute this to. This maybe is classical. If you have a degree 4 polynomial and you take y squared equals that, so that's a genus 1 curve, and then you take y squared equals x times that, this is a genus 2 curve. This genus 1 curve and this genus 2 curve glue to this genus 3 curve. Y squared equals P4 evaluated at x squared. Notice this thing has a non-hyperelliptic involution. X goes to minus x. And so when you divide by that, you get back C1. And okay, so here's a bunch of examples that you can cook up that achieve various maximal Sato-Tate groups of abelian threefolds using curves of this particular form. So these are hyperelliptic curves with this involution, and yeah, the genus 2 curve has 2 rational Weierstrass points, right? 0 and infinity. So these are quite special. So you don't expect to be able to do everything this way, but you get a lot of the, so to speak, easier cases where the component groups are not very large. You get a lot of the cases in this fashion. So this updates the scoreboard quite a lot. I tick off a lot of these cases where I don't have, I have some CM factors maybe, but not huge numbers of CM factors. But these cases lower down remain somewhat mysterious at this point in the talk. So I'm running very short on time. So maybe if there are questions at this point, I should just hold them until the end, unless they're urgent. So let me go through the next couple of sections very quickly, and then we can have questions. So this is another slide you might want to look at on your own time. I'm just going to flash it to illustrate, but I'm not going to go through it in detail. This is the tabulation of reduced automorphism groups of genus 3 curves. So this is classical. I don't remember the attributions for this. Reduced means I divide by the hyperelliptic involution, if there is one, because that kind of makes the parallelism better. These groups, the more complicated groups, I use gap notation to describe them. And over here, what I give you is, if you take a generic curve of one of these forms, I can tell you what the connected part of the Sato-Tate group is going to be. And so these are indices into my earlier table. So basically the strategy in this part of the talk is you use these examples, maybe, but not with automorphisms realized in a nice way, twisted so that the automorphisms are hard to write down, so precisely so that they become defined over some very large field. So you get some very large Sato-Tate group. So for example, if you consider this hyperelliptic curve, this is one of the maximal automorphism groups of a genus 3 curve. This has reduced automorphism group S4. The twists of these curves were classified by one of Drew's 2016 Arizona Winter School project groups, which Victoria was a part of. And these give you examples where you get an extension of SU23 with the group S4 acting. So similarly, in this case, you get reduced auto. So this is a curve with reduced automorphism group D6. Twists of this give you one of the maximal groups that extends U13. And then you get some other cases maybe that are more familiar by twisting the Fermat-Klein quartics by their automorphisms groups. So Drew and Francesc worked out examples of these twists that give you maximal extensions of U13. So these are cases where you take curves that have automorphism groups that are maximal among genus 3 curves. But it's also profitable to look at families of curves that acquire smaller automorphism groups. So Elisa Lorenzo Garcia has classified twist families, sort of maximally generic twist families for various automorphism groups. So for example, if you take curves with automorphisms by S3, this is not the maximal family, but this is a family you can write down that have an automorphism by F3, but over an S3 cubic. So these give you cases where you get SU23 with the group D6. Right, the extra factor of 2, the extra factor of 2 is coming from, you get 2 curves with the same J invariant, but they're quadratic twists of each other. Oh yes, Elisa was also part of, sorry. So right, I'm missing Elisa's name on this slide. Sorry, Francesc. Sorry, Elisa. It would have line route. Oh, sorry, he means here. Yes, sorry. This slide should, Elisa should be part of this collaboration on the bottom of this slide here. My mistake. This one was Francesc and Drew. Yeah, okay. So for another example where you get large extensions using non-maximal automorphism group, if you take y to the 4th equals a quartic, these are D4 extensions. These are D4 quartics. If you take a generic twist, a generic example in this family, you get SU2 cross U12 extended by J of O. So this looks like taking a non-CM curve times a genus 2 curve with the maximum possible Sato-Tate group for a genus 2 curve. So these things actually, you actually get Jacobians that look like those products. I'm not claiming that this thing actually maps to a Jacobian of a genus 2 curve, because the genus 2 curve in this case might be decomposable. I think it actually is decomposable. So, so I'm not claiming this is actually a gluing of a genus 1 curve and a genus 2 curve, but it looks like such a gluing. Yeah, so that's what's going on this side. So this is sort of the generalization of the gluing that I talked about earlier. If you take a plane quartic with an involution, this is a double cover of a genus 1 curve, and you can write down some examples of things that are where one of the variables only occurs to even powers. I forget which variable it is. I think it's y in both of these cases. So these are examples that we got by searching through data to look for cases that putatively match these groups, but then you can use rigorous calculations to match these. And so, yeah, so in this case, the genus 2 factor here is not guaranteed to be principally polarized. It's a 1-2 abelian surface, which is a prim for this ramified double cover. You can say that it's isomorphic to a Jacobian of a genus 2 curve, but without its polarization, maybe also without its base field. I mean, you might have to make a base field extension, and you might get decomposability here. So you should really think of this as 1-2, but it's an abelian, an elliptic curve times an abelian surface. I should mention that Drew found those examples using a ginormous Google Cloud Platform run. This is sort of a typical example of how many CPUs he was running on. So this is 2 million up here, and this took a couple of hours. This is minutes, I think. And these are locations around the world. I'll let you admire that on your own time. But so this is basically the final scoreboard. And you see that there's something missing here. I skipped cases of CM elliptic curve times sort of a genus 2 curve with maximally CM Jacobian, and I skipped the full CM case. I wasn't able to do all of these cases. So these cases, let me just flash to my final, let me just flash to, maybe I should just leave this, maybe I should leave it like this. So I'll say in words, that, and we can, if there are questions about this, I can use the extra slides. These cases, I have basically no idea what to do. There seems to be an obstruction to realizing these with Jacobians. There are more cases that I can realize with principally polarized abelian varieties, but not all of them. And so there seem to be some cases where I seem to be forced to take polarizations with a 2 or a 3 in the degree, but this is not completely understood. So I'll stop for now, and if there are questions about any of this stuff that I mentioned at the end, we can do that. I'll stop there.
Okay, thank you very much, Kiran, for this wonderful talk. Are there any questions?
I have a question.
Yes, please.
Ron, go ahead.
I was just wondering, I mean, this might be a naive question, but I was just wondering, since you've done a beautiful classification of all the possible Sato-Tate groups that could arise by looking at these curves, are there new cases of the Sato-Tate distribution that you can establish using existing knowledge but what weren't known before? For example, you know, cases of curves where you'd get, you know, I'm saying don't cheat, like don't take products of elliptic curves, but take some curve in which you would get something like a type H, you know, when you had U1 cross U1 cross U1, or a type G where you had U1 cross U2, I think, or something like that.
Yeah, so there are a few cases. I don't think this space has been explored very much. To investigate that question, you know, for which curves it's feasible to prove the Sato-Tate conjecture, right? So that depends on essentially. So you have to exclude USB6, of course. I'm not sure whether you can. I don't think you can maybe deal with U of 3 either. And you have to avoid these cases that have a USB4 factor. So basically start with this line. Things on this line and below, you have some hope, although this line is quite difficult. My understanding is you can maybe make a little bit of progress using triple product L functions, but I don't think you can get much further than that. These cases with the 2 SU2s are going to be tough. The case with 1 SU2 and other U1s, these are quite good candidates to use modularity lifting or potential automorphy techniques.
Yeah, I'm thinking that the case F is also doable.
The case F, I believe, is also doable, right? So I think it was Michael Harris who noticed that you can do S, and then I think Christian Johansson and Johan Taylor worked at the details. Francesc knows this better than me. Yeah, for SU2 cross SU2, those cases are largely tractable in the abelian surface case. So I suspect U1 cross SU2, those kinds of things should be.
Yeah, that'll just be Rankin-Selberg in that case. Yeah.
Yes, that's right. Yeah. So yeah, but yeah, for 3 SU2s, it gets into the triple product, and that I think you just get much less mileage that way.
Perfect. Thank you for your question. Are there any other questions? Okay, so perhaps you can develop a little bit.
There's a question in the chat.
Oh, sorry.
In the Q&A.
Perfect.
So the question, it appears to be, are all the connected? Oh yeah, let me go back to slide 11.
I can, yeah.
Yeah. So the question says, if I go to slide 11. So the question is are all the, maybe the questioner can unmute and ask the question live.
For sure.
So I can sort of follow the questions.
So, Sangshuan, can you raise your hand eventually? Okay, I can allow you to speak.
Okay, I should be able to speak now.
Yes, I can hear you.
So here you just classified all the connected components of the Sato-Tate group. So, but also there is the component group. These are the finite groups. And in the
so do you need for
this? I assume that it's in the paper somewhere.
Yeah. So if you're asking about threefolds, that's slide 13.
Yeah, I see that.
So we do describe, so for these cases, we describe the component groups, but we're doing more than that, because just telling you the connected part and the component group is not complete information, because there's an extension problem you have to solve. So we are actually solving the extension problem as well. So these are classified as conjugacy classes of subgroups in USP6. So we have the component groups classified and the extension problem classified.
Okay, well, thank you. And can I ask one more question, quick one?
Yes,
so
please.
You have already done the dimension 1, dimension 2, and now dimension 3. So you already have enough information. And the question is that go from the lower dimension to the higher dimension. Have you observed any? Probably you are already thinking of that. Whether that will produce a large number of them, and whether you can find the.
Yeah. So you're asking about, like, if I look at dimension 4, but I don't worry about the indecomposable cases, I just look at product cases.
Mm-hmm. So from the lower dimension and taking product go up, that will produce lots of cases, making the dimension.
Yeah, so it would be interesting. I haven't tried to do this, but yeah, with the data we have, of course, in principle, one could take all of the products to go up to, for example, dimension 4. We have the information to do this. I haven't had the stamina to try, but I would encourage somebody who has more stamina than me to look at products of lower dimensional things in, for example, in dimension 4, and to see what cases can occur for Jacobians of hyperelliptic curves, Jacobians of non-hyperelliptic curves, prim varieties, other things that can be realized explicitly.
Yeah, I mean, the philosophy is very similar to the representation of the Lie groups. You go from Levy subgroups, you do some kind of a parabolic induction, you get to the higher, for the larger groups. And so the picture you have already presented seems to be, at least that's a natural question to ask.
Yes, I mean, there's nothing parabolic in this story because everything is compact Lie groups. So
that's correct.
But there are these finite group problems that are quite interesting to study. Essentially, the classification problem boils down to problems of, not literally problems of finite group theory, because things are sitting inside these ambient groups and you need to solve these extension problems. But essentially, these are classification problems for finite groups. And I find finite group theory quite hard. So I don't know how much stamina I have to go further. Really, one really needs to automate this, put some of this on a computer. Right, there are good programs for example, finding maximal groups, say finite subgroups of GLN over the integers. So you need to use technology like that in order to attack higher dimensional versions of this problem. This is not going to be solvable by hand.
Okay, thank you very much. I appreciate it. Very nice, very interesting talk to me.
Well, thank you very much for your question. Okay, I think we can thank Kiran again for the nice talk.